So we're going to go over AP calculations. For the example where we have a purified pool of alkaline phosphatase, it has volume 10.4 milliliters, and we have measured two kinds of absorbance measurements. Right? So we have absorbance at 280 was measured, and that was undiluted fraction was used for that measurement. And we also have absorptivity, need units, mil per meg centimeter. And this absorptivity is predicted based on amino acid composition of alkaline phosphatase. I'll show you later how to use a program that can do it. It's called prot_param. If you have amino acid sequence, you can predict that. Okay, and so think about that we have purified this tube with 10.4 milliliters of enzyme. We're probably going to keep it on ice, right? And this is our kind of stock of the enzyme. The other kind of measurement we're doing involves activity assay, where we're just pipetting the purified enzyme into a cuvette, right? And the cuvette has assay buffer. So I'll put here, so we have 0.9 ml of buffer plus substrate P and PP, paranitrophenol phosphate. And then we're going to add to it during this assay 0.1 ml of enzyme. And in our case, it's undiluted, but a lot of the time you have to dilute the enzyme before you add, right? So from this, one of the things that's important, we have assay volume, which is 1.00 milliliter, right? And the volume of enzyme in that assay is 0.1 milliliter. So we have like 3 different volumes we're tracking. Total volume of all the purified enzyme, right? Then we have 0.1 milliliter of enzyme goes into activity assay. And then we have assay volume is 1 milliliter. It will become important as we think about our calculations. So we are detecting appearance of paranitrophenolate ion, which is deprotonated form of the product of hydrolysis from PNPP to paranitrophenol, right? And so we measured its change in absorbance per minute. So as we go through the calculations, pay attention to whether we're talking about the original stock of enzyme or the assay that we're doing, right? And like what kind of concentration or volume do we need to put in? All right, so let's review what we're going to calculate. And I'm going to just list things here. So we're going to do, figure out first concentration of protein. In the original tube. Then I'm going to also put to concentration of protein in the assay, right? So in the cuvette, one is in the original tube, the other in the cuvette. Then next, we're going to be thinking about velocity in the cuvette. That's the velocity of reaction catalyzed by our enzyme. And then related to that is going to be units of activity. So actually, let me write that. Activity in international units of activity in the tube. Actually, first let's do in the cuvette. We will also figure out IU per mil of undiluted enzyme. or AP, that's we purified. Okay, and then from there, we're going to be characterizing the stuff that's in the tube. So we need specific activity. Okay, so, and again, the one before U per mil is activity per mil. Right, and then specific activity is going to be IU per mg protein. That's one way we can judge purity. The higher the specific activity, the more enzyme you have. And then I'm adding a couple of more things to this. Let me see, and I will just do this. So we're going to think about how we're measuring this. So the other thing is I want to see what we have for active site concentration. So how many active sites is present in solution. So we're going to measure that in micromolar. And the last one, 7, 8, this is my 8, is going to be, can we estimate kcat, which is a turnover number, right? So this is turnover number. And I'm hoping we can compare that number to the literature to see, is our measurement reasonable? Is our assay working? Is it similar to what people find in the literature? Now, I left those in black ink, whereas others I've tried to color code based on where, which, I don't know, which tube or cuvette we're measuring. Okay, so let's kind of move forward. Hold on. Let me scroll up. Oh no, I need more pages. I'll pause for a second. Okay, so I've got some more pages here. So let's start with number 1, protein concentration. That's going to be related to the absorbance at 280, right? And A equals ECL. So concentration of protein C equals absorbance divided by E and L. And so I'm gonna think about what that is. 0.487 absorbance units divided by 0.7002 mil per meg centimeter times L is 1 centimeter, which is a path length, right? So the centimeters cancel out. And we're gonna have, where's that number? 0.694 mg per mil, right? Write that down. Okay, so now if we think about what's the protein concentration in the assay, right? We're gonna put 2. We used 0.1 mil, so I'll put 0.1 ml, which is our C1 times, V1. Fix that. V1 times C1, 0.694 mg per mil equals 1 milliliter in the assay times X, right? So solving for X, 0.0694 mg per mil in the assay. That's our cuvette. We're doing that, and it will come in handy later. Okay, so next, number 3 is going to be velocity in the cuvette. So we're going to compare with it. 3, velocity in the cuvette, and we're still relying on Beer's law to convert velocity that we measured, which is the slope we got from spectrophotometer, delta absorbance over time, over delta T. We want to convert to delta concentration over time, delta T. And the concentration here, notice, is not the protein, it's the concentration of PNP minus, right? Pyranitrophenol concentration of product. But the conversion is going to be the same. Concentration is absorbance divided by absorptivity and path lengths. So I'll start the conversion here. Velocity equals, so we're going to start with the number we have, 0.9573 absorbance units per minute, right? And then we put the absorptivity of pyranitrophenol 1.64 times 10 to the fourth, and this is in units of molarity, -1 centimeter, -1, so they go on top, right? And then we also need 1 centimeter here. So let's cancel out the units we don't want. And we'll get molarity per minute for units of velocity. And let me write that down as 0.584 molarity per minute. Oh, sorry, forgot the factor here, times 10 to the -4 molarity per minute. And to convert it into scientific notation, right? So it's going to be equal to 5.84, 10 to the -5, and I'll write this out as mole per liter per minute, right? That's the molarity units broken out. All right, so that is our velocity in the cuvette. And from here, the force measurement, or first calculated, is going to be activity. And activity measured in international units of activity is basically, we need to convert velocity to get rid of the volume in there. So activity is going to be measured in terms of micromoles of product produced per minute, micromoles, not micromolar, okay? And so generally, it's going to be velocity in the assay times volume of the assay. All right, so from here, let's put some numbers in. 5.84 times 10 to the -5, and I'll put those units moles per minute per liter, right? And then our assay volume is going to be 1 milliliter. And then we want to convert some units, which would be 1 liter is 10 to the 3rd milliliters, right? And we need to convert our moles into micromoles. So I'll put this on here, 10 to the 6 micromoles is 1 mole. Right? So this is unit conversion. So liters should go away, milliliters should go away, and moles go away. So we should be left with micromole per minute, right? And this is micromole of product per minute. All right, so if we do this calculation, I'm going to have 5.484 times 10 to the -5, 10 to the -3, 10 to the 6 micromole per minute. Okay. And that should be 5.84 times 10 to the -2 micromole per minute, right? That's how many units of activity we have. And this is in our assay in the cuvette, right? We used the volume of the assay. Okay, so now we're thinking back from the cuvette. So what's going on in the cuvette? Let's figure out what's going on in the tube of enzyme that we purified. And so for the fifth one, we want for undiluted enzyme, how many units of activity per mil of undiluted enzyme. And that should be equal to activity in the cuvette divided by volume of undiluted enzyme, volume of enzyme added to cuvette, right? And then usually times dilution factor, because if you dilute it tenfold, undiluted will be tenfold higher. But in our case, dilution factor is just 1, so we can multiply by 1, nothing changes. Okay, so in this case, our IU per ml is just going to be 584 times 10 to the negative 2 IU, right? So these are micromolar product per minute as IUs, divided by 0.1 milliliters of enzyme in the assay. And we will end up with 0.584 IU per ml of undiluted stock. Okay, so let me just back up, make sure micromole of products produced per minute, 1 micromole per minute is 1 IU. So these are our units of activity, IUs. Okay, so next we're ready to tackle specific activity, because specific activity involves, write that down, specific activity. And we basically need IUs per mg. So for every mg of protein, how many units of activity do we have, right? And to do that, for us, the easiest is to just go IU per ml divided by mg per ml. So we take undiluted, so we take item 5, IU per ml of undiluted, and divide by concentration of protein undiluted. And in our case, we didn't dilute anything, so it's a little easier. So I'll write that as 584 IU per ml divided by 0.694 mg per ml. Mils will cancel out, and we should get 0.841 IU per mg. So hopefully it's clear that this is from number 1, is it? Yeah. And this is from number 5, we calculated. All right, so next question is a little bit trickier. Now we want to know how many, or what's the concentration of active sites in our solution. And we want to know that because we're going to use it for estimating KCAT later on, right? So let me scroll up. So let's think about with the enzyme for active sites. Are we talking about protein or the cuvette? And what kind of measurement should allow us to determine that? So I'll put 7 here. Right, that's active sites concentration in our undiluted enzyme solution, and we want this in micromolar. Right, so what we have is protein concentration in mg per ml, and we want to convert it into active site concentration. So we're going to assume that there is 1 active site per subunit. And we also know that there is 2 subunits for each molecule of AP. Okay, so that part you have to search in the literature. If you look that up, you see that this protein alkaline phosphatase is a homodimer, and each subunit is 47.2 kilodaltons, right? But there's 2 of them. And so that's information you would search in UniPro database when you're studying a protein. Hopefully, if someone already studied it, you know. If this is a protein you're studying for the first time, you kind of have to go figure that out. Okay, but for us, basically, we're going to make assumption that in our purified protein preparation in the pool, all the protein we have is AP. That's an assumption we make. And so we're basically just doing unit conversion to micromolar. Mg per mil convert to micromolar. And for that, we're going to need molecular weight. And with molecular weights, 47.2 kilodalton is 47,200 daltons, which is also gram per mole. So that part is helpful. Right? So we just need to convert mg per mil into micromolar. All right, so concentration, let's see. Concentration in mg per mil is going to be 0.694 mg per mil. And we're going to convert that into 47,200 gram per 1 mole. That's molecular weight. And then we need to convert moles into micromoles, right? So it's going to be 10 to the 6 gram per mole, milliliters. I think I'm okay, micromole to 1 mole. And let's see what we got. Oh yeah, we still have mg per mil is the same as gram per liter. So I can't just replace that because mg and mil, you know, that will cancel out. So this is the same as saying grams per liter. So I'm just going to replace that. I'm too lazy to do 10 to the third on top and the bottom. Okay, so with that, grams cancel. Liters not going to cancel. Let me keep that. Oh, moles will cancel, right? And so we'll end up in units of micromole per liter, which will give us micromolar. Okay, so put the calculation here. If you plug that in, you should get 14.7 micromole per liter, or micromolar, big M, right? And I'm sorry if this is kind of jumping, but mg per mil is the same as gram per liter, right? So mg is factor of 10,000 cancels out. Okay, so the last part, now we're going to think about, can we estimate kcat? No, so I don't screw this up, 8. Is kcat, or turnover number. And the meaning of it is how many molecules of product can be produced per unit time by one active site, right? So we're really now working on a molecular level. We're thinking about each molecule of enzyme, except each active site. If you have a dimer, it's a little trickier. So for each active site on the enzyme, how fast can it go? And the key to this is when the enzyme becomes rate limiting. So this is kcat is at saturation when the enzyme is limiting, right? And kcat equals to Vmax divided by concentration of enzyme total. Except, again, with a dimer, it's a little tricky. We're actually thinking concentration of active sites here in order to get this rate at saturation per molecule of enzyme. So the first question should be, when we measure velocity, the velocity we have, is it equal to Vmax? Right? Is that true? And the answer to that is maybe. And the maybe is there's an assumption that we make when we do these activity assays. We set them up so that the substrate is not rate limiting, because we're trying to gauge how much active enzyme you have. So the enzyme has to be rate limiting, right? And that by definition is when you saturate with substrate, then you have the enzyme rate limiting. So if our assay is set up correctly, we should be using saturating substrate concentration, right? And that's another reason why if you do the assay, and the velocity might be too high, you may have to dilute your enzyme because the enzyme needs to be limiting, right? And then for which concentration of enzyme should we use? So like maybe we are going to do that. Then we need to think, is it going to be 14.7 micromolar? Okay, so I'm going to look back. I think the velocity we measured, right? This is going to be in the cuvette. In the cuvette, velocity, and that was calculated in like item 1 or 2. I forgot now. So where is it? Let's scroll back. Velocity in the cuvette, right here. Right, so it's item 3, and we have the velocity 10 to the minus 5. Okay. Let me put here. So kcat, given the caveat that we're making assumption, is going to be 5.84 times 10 to the negative 5 molarity per minute. Right, and now we need to divide it by enzyme concentration or enzyme active site concentration, right? And notice if we're working in the cuvette, concentration of active sites is not 14.7. It's going to be 1/10 of that, right? So it's going to be 1.47 because we used 0.1 ml of undiluted enzyme into 1 milliliter of assay. Okay, so we're dividing it by 1.47 micromolar. So we need to figure out get rid of the micro, right? Actually, we'll do it this way. So 1.47 micromolar is 10 to the minus 6 molar, right? And then the molar will cancel out. And our answer, kcat, is going to be 3.97 times 10 to the minus, actually when the 10 to the minus 6 goes to the top, it's just 10 to the 1. 39.7 per minute. All right, so the question becomes, is this reasonable value for AP? So what we're saying with this kcat is about 40 molecules of product will be produced each minute by 1 active site, right? Is that a reasonable velocity at saturation? The substrate is plentiful, if substrate is not limiting, and the enzyme goes as fast as it can only go 40 molecules of product per minute. Is that reasonable, right? Is it good for an enzyme? So that's something we can discuss in class, but I hope you look that up, and we calculated that so we can look in the literature and see how does that compare to what other people found.